Above the sun's bright skin floats a white crown that burns far hotter than the fire below it. That is not how heat is supposed to work, and it is not what anyone would expect from a star. Stay with me because this is one of those space stories that sounds impossible until the evidence starts piling up. But first, subscribe if you want clear space stories like this landing in your feed before the next mystery slips by. Most of us grow up with a simple picture of the sun, a giant hot ball, brightest in the middle, cooler as you move outward, and quiet only from far away. That picture is useful, but it leaves out the strangest part. The sun does not only shine like a lamp, it also behaves like a machine made of heat, motion, and invisible ropes of magnetism. If you could peel away the blinding light we call the surface, you would not find calm. You would find gas boiling, twisting, snapping, and rising like water in a pot that never stops. And above all that, so thin it should be cold, hangs the corona. That is the sun's outer atmosphere. It can reach around 2 million degrees Celsius, while the visible surface is closer to 5,500 degrees Celsius. During a total solar eclipse, the moon blocks the bright face and that hidden crown appears. It does not look like fire from a stove. It looks like white silk pulled into the dark, with long streamers stretching into space. Ancient skywatchers saw beauty there. Modern scientists saw a problem that made no sense. Imagine standing near a bonfire and getting warmer as you walk away from it. That is the rough picture NASA gives when it explains this mystery. It sounds like a joke the universe is telling on physics, but it is not a joke. It is one of the longest running puzzles in solar science. Now let us start from the beginning. The first thing many people believe is wrong. They think the sun's surface is the hottest part because it looks the brightest to our eyes. But brightness is not the same as temperature, and the surface is not the core. The light we see comes from a layer called the photosphere. Above it sit other layers, and those layers are ruled not only by heat, but by magnetic energy. Another common mistake is thinking space near the sun is empty, in the simple way a blank room is empty. It is not. The corona is thin, yes, but it is full of charged gas called plasma, which is gas so hot that electrons break free. Plasma listens to magnetic fields the way iron dust listens to a magnet on a table. That changes everything. It means energy can move in ways your kitchen stove never could. For a long time, the corona itself was the underdog of solar science. People noticed the bright disk, the sunspots, the flares, and the seasons on Earth. The faint halo around the sun during eclipses looked pretty, but almost decorative. It was like the soft light around a lamp in fog. Nice to see, easy to ignore. Then came the first surprise. Scientists expected that strange glow to be ordinary sunlight from ordinary gas. What they actually found was a weird set of colors, or spectral lines, that did not match familiar elements on Earth. It was like hearing a piano play a note no piano should be able to make. For a while, some thought the corona held a brand new element and called it coronium. That idea felt exciting, but it was wrong. The real answer was stranger and more important. In 1941, the Swedish physicist Bengt Edlund showed that many of those lines came from familiar atoms like iron, but in a wildly stripped state. That means the atoms had lost many electrons. To do that, the gas had to be blisteringly hot. This was the second beat of the surprise. Scientists expected an unknown substance. They actually found ordinary matter pushed into extraordinary conditions. Picture a simple metal pan from your kitchen, not changed into magic, just heated far beyond what your oven could ever do. The mystery shifted in one stroke. The question was no longer what the corona was made of, but how it got so hot. That shift mattered because it turned a naming problem into an energy problem. And energy problems in space are often magnetic problems. The sun is not just hot, it is churning. Hot plasma rises, cooler plasma sinks, and all that motion drags magnetic fields around like spoon strokes through thick soup. The first major idea grew from that fact. And the first surprise after Edlund's work was that the sun might be heating its atmosphere with waves, not just with direct heat. Scientists expected heat to leak upward in a smooth way. What they found instead was a star that may send energy upward through magnetic vibrations. In 1947, Hannes Alfvén described a kind of wave that can travel along magnetic fields, and those waves now carry his name. An Alfvén wave is a wobble in magnetized plasma, a bit like a plucked guitar string, except the string is invisible and millions of miles long. NASA describes one version of the idea with a surfer image. Ocean waves push surfers toward shore. Magnetic waves may push energy into the corona. It is a beautiful idea, and beauty matters in science, but beauty is not enough. You still need a way for those waves to dump their energy as heat. A bell can ring without warming a room very much. A guitar string can hum without boiling water for tea. So the hard question became this: how do waves stop being motion and start being heat? The second major idea sounded more violent. Maybe the corona is heated not by smooth waves, but by countless tiny blasts. In 1972, Eugene Parker proposed nanoflares. The name makes them sound small, and they are. NASA says they are about 1/1,000th the size of a normal solar flare, but tiny does not mean unimportant. Think of drops of water on a window. One drop does not soak the ground. 10,000 drops over time can. That was the logic. Scientists expected the corona might be warmed by many little events too weak to notice one by one. What they actually started started hunting for were sudden magnetic snaps, each dumping a small packet of energy. Magnetic snapping has a plain language name in solar science. It is called magnetic reconnection. That means magnetic field lines get twisted, pushed, and forced into a new shape, then suddenly realign and release energy. NASA compares it to an overwound rubber band that finally snaps. You cannot see the field lines with your eyes, but you can see what the released energy does to the plasma around them. By now, the story had two strong suspects. Waves could carry energy upward, nanoflares could release energy in bursts. Both ideas had logic, both matched parts of the evidence, and for years, neither side won cleanly. The sun kept its mouth shut. If you had to picture the problem at that stage, here is a simple way. Imagine hearing loud footsteps upstairs every night. One person says it is pipes rattling in the walls, another says it is someone dropping boxes on the floor. Both can make noise. But unless you go upstairs, you are guessing from the kitchen. Would you tell me in the comments which sounds more convincing to you right now, waves or tiny magnetic blasts? Your comment helps me see which kind of mystery you want me to unpack more deeply in future stories, because from here the evidence starts getting more exact. To test a mystery like this, scientists had to stop treating the sun like a flat yellow circle in the sky. They had to measure layers, speeds, delays, and changes in tiny patches of plasma. That meant space missions, better telescopes, and a lot of patience. The corona is bright in some ways and faint in others. It is like trying to study steam above a pot, while the stove light is shining in your face. One big clue came from watching loops. These are giant arcs of glowing plasma shaped by magnetic fields. They rise and bend through the corona like shining bridges. Scientists expected them to be simple tubes of hot gas. What they actually saw were structures that flickered, shivered, and changed on very small scales. Another clue came from timing. If energy starts low and heats the corona later, there should be a delay. Not a vague feeling, a measured delay. A few seconds can matter. That is the difference between hearing thunder after lightning and hearing a door slam in the next room. NASA's Interface Region Imaging Spectrograph, called IRIS, became a key player here. It was built to zoom in on hard-to-see events in a small part of the sun. On April 3rd, 2014, during an event called coronal rain, researchers noticed tiny bright jets. Coronal rain is cooled plasma falling back down almost like a glowing waterfall. Near the end of that event, something fast and sharp lit up. The third discovery puzzled scientists in a very useful way. They expected a messy blur. They actually saw clear nanojets, thin, bright streaks moving across magnetic structures in the corona. NASA wrote about this on September 21st, 2020, when a Nature Astronomy paper reported the first clear images of them. These looked like a smoking gun for nanoflares. Not proof of the whole case, but a fingerprint at the scene. The 3-beat pattern mattered again. Scientists expected tiny events to stay hidden. What they actually found were bright, bursty signs of magnetic reconnection. The simple comparison is sparks jumping from a frayed wire, except the wire is the size of a world and the sparks shape the air of a star. One reconnection may trigger another. That creates an avalanche effect. IRIS was not working alone. Researchers also used NASA's Solar Dynamics Observatory in the High Node mission, a partnership that includes JAXA, ESA, and NASA. They were trying to see not just the flash, but what happened above it. Did the energy stay local, or did it reach the corona where the real puzzle lives? That was the whole point. A NASA report on another study went even deeper. Lead author Shaba Howden of the Laboratory for Atmospheric and Space Physics at the University of Colorado Boulder studied tiny bright loops below the corona. He and others noticed something odd. Some heavier elements were racing out at about 60 miles per second. Lighter ones were not behaving the same way. That was not what anyone expected. In everyday life, a lighter ball usually moves more easily than a heavy one. So scientists expected lighter ions to respond more strongly. What they actually found was the opposite pattern in those loops. Amy Weinbarger of NASA's Marshall Space Flight Center said that clue forced them to rethink the heating process. Something selective was happening. The explanation that fit best was magnetic reconnection. Howden spent years testing different possibilities with computer models. In the end, the model that matched the strange behavior was the one where a reconnection event creates a brief electric field. Heavier ions could keep moving through that field and steal more energy. It is like a strong runner pushing through a crowded hallway while smaller kids get stopped. Then came the timing test. Using NASA's Solar Dynamics Observatory, Howden looked at the coronal region above the brightening. The report says the corona heated up after only about a 20-second delay. That is precise enough to matter. It is like hearing a microwave beep and then almost at once feeling steam when the door opens. Energy had moved upward fast. This was powerful because it followed the full surprise pattern. Scientists expected maybe a local flash with little wider effect. What they actually found was a tiny low structure that seemed able to feed super hot plasma into the corona. The household comparison is a single crack in a pipe heating the whole radiator line above it. Small trigger, large result. But before we hand the whole case to nanoflares, another set of clues pulls us back. Some parts of the corona do not look bursty at all. They look steady, calm even, and steady light is awkward for a theory built on constant tiny explosions. That tension keeps the story alive. ESA's solar orbiter has been watching this from a different angle. ESA says the spacecraft launched in February 2020 and carries 10 instruments. It gets closer to the sun than Earth and studies the corona, the solar wind, and the sun's magnetic cycle. Its routine science work began in November 2021. It is one of the best tools we have for catching the sun in the act. One solar orbiter science result raised eyebrows for a simple reason. The loops look too steady. On a page from ESA's solar orbiter team, scientist P.G. Judge described large areas of coronal loops with only about 1 to 2% brightness changes. That is tiny. About the kind of change you might miss if your bathroom light dimmed for a blink. If those steady loops are really powered by classic nanoflares, then a huge number of bursts would have to overlap along our line of sight. The ESA write-up says around 10,000 energy quanta would be needed in some cases. That is a lot, so maybe the energy packets are smaller than the old picture suggested. Maybe not nanoflares, but picoflares, around 10 to the 21 erg instead of 10 to the 24 erg. That does not kill Parker's idea. It sharpens it. Scientists expected one neat answer. What they actually found may be a family of answers, with events of different sizes and rates. Think of rain. Sometimes you get a few fat drops on a window. Sometimes you get a fine mist that still leaves the whole glass wet. Would you tap like on this video and tell the channel why this puzzle matters to you? That signal helps the YouTube system notice that careful science stories are worth showing to more curious people. And the next clues make the puzzle even richer. Now enter the boldest mission in the story. NASA's Parker Solar Probe was built to go where no spacecraft had ever gone, not near the sun in a loose way, into the corona itself. The mission page says it launched on August 12, 2018 at 7:31 UTC. At first glance, that sounds reckless. The sun is the thing you do not touch. That is the oldest rule in the room. But Parker Solar Probe was designed for this exact job. It carries a carbon composite shield 4.5 inches thick. NASA says that shield can handle nearly 2,500 degrees Fahrenheit. The probe is also absurdly fast. NASA says at closest approach it moves around 430,000 miles per hour or 700,000 kilometers per hour. That is fast enough to get from Philadelphia to Washington, D.C. in about 1 second. Numbers like that help your brain grab the scale. Without them, space missions can feel like cartoons. With them, you start to feel the rush. The fourth major discovery was not a photo, it was a crossing. Scientists expected Parker to approach the sun and gather indirect clues. What actually happened, NASA announced on December 14, 2021, was that the spacecraft had flown through the sun's upper atmosphere in April 2021. Humanity had, in a real and measured sense, touched the sun. Not the bright surface, but the corona. That matters because once you are inside the corona, you are not guessing from far away. You can sample particles, you can measure magnetic fields, you can watch where boundaries rise and fall. It is like standing in the fog instead of staring at it from the road. Suddenly the air itself is evidence. And what Parker found was not a neat shell with a simple edge. The boundary of the corona appeared wrinkled and uneven. There were switchbacks, sudden zigzag changes in the magnetic field. There were places where the solar wind seemed to start in bursts and places where the magnetic geometry was more tangled than expected. The sun was not handing over one clean mechanism on a silver tray. This is where the underdog part of the story comes back. For years, the corona was the faint halo people admired during eclipses. Now it was the place dictating the behavior of the solar wind that washes across the whole solar system. ESA says Solar Orbiter studies how that wind forms and reaches hundreds of kilometers per second. The quiet crown had become the driver of space weather. Space weather sounds gentle, but it is not always gentle for us. Changes from the sun can affect satellites, radio signals, and power systems. So this is not just a puzzle for people in observatories, it is a practical mystery, like not knowing why the wiring in your house keeps surging during storms. You do not ignore that. As the evidence grew, the dates got sharper. The old puzzle was recognized in the early 20th century. Edlin's key paper came in 1941. Alfvén's wave work came in 1947. Parker proposed nanoflares in 1972. IRIS caught a key event from April 3rd, 2014, later discussed by NASA in 2020. Parker Solar Probe launched on August 12, 2018, and crossed into the corona in April 2021. That kind of timeline tells you something important. Science does not solve hard problems in one leap. It solves them in layers, a strange color in one era, a theory in another, a spacecraft decades later, a measured delay of 20 seconds that suddenly changes what is possible. Then a new layer arrived from Nature Astronomy in 2024. Researchers studying an active region on the sun looked at something called moss. That is the bright, patchy glow seen at the foot points of hot coronal loops. The word sounds soft, like something on a whetstone. But on the Sun, it marks places where heating and magnetic structure meet. The team used data from the Hi-C 2.1 sounding rocket and from IRIS. The Nature Astronomy paper says Hi-C 2.1 launched on May 29, 2018 at 1854 UT. It observed active region A R12712. Its flight lasted 335 seconds, just over 5.5 minutes. A kitchen timer can last longer than that, yet those minutes carried huge value. Scientists expected heating in the lower atmosphere and heating in the lower corona to be only loosely linked. What they actually found was a tight connection. The signals matched in space and time down through several layers. The simple comparison is seeing lights flicker in the basement and attic at almost the same moments, telling you the same wiring may feed both, and that pointed again to a common magnetic cause. The models in that study added another piece. They suggested that deep magnetic braiding creates thin current sheets. A current sheet is a narrow zone where electric current gathers and magnetic energy can be released. Those sheets can extend from the chromosphere into the corona. When they break down, they heat plasma along the way. That is less like one bomb going off and more like a twisted cord heating where it frays. If that is right, then some wave ideas and some burst ideas may not even be enemies. Braiding creates stress. Stress creates current sheets. Current sheets can reconnect. Reconnection can launch waves. Waves can reflect and crash into each other. The sun may be using several linked processes at once. And this is where scientists will tell you they do not fully understand it yet. That line matters, not because the mystery becomes spooky, but because the models had predicted simpler behavior in places where the real sun looks mixed. Some regions seem impulsive, some seem steady, some may be heated from below, some may be heated by turbulence building higher up. One of the newest clues comes from the laboratory, which sounds almost funny. How do you study the sun in a lab on Earth? Not by making a tiny sun in a jar, by making the right kind of plasma and magnetic behavior. If you can reproduce one piece of the physics, you can test whether the idea even works. In 2024, Princeton Plasma Physics Laboratory wrote about results led by Sayak Bose. The team used the Large Plasma Device at UCLA, a plasma column about 20 meters long. They were studying coronal holes, which are lower density parts of the corona where magnetic field lines open out into space, and these regions help feed the fast solar wind, and they may hold another part of the heating answer. Here was the fifth discovery. Scientists expected Alfvén wave reflection to be a nice theory that was hard to prove directly. What they actually demonstrated in the lab was that Alfvén waves can reflect when they pass through changes in plasma density and magnetic field strength, like those near coronal holes. A good home comparison is a hallway echo, where sound bounces back when the space changes shape. Only here the echo can stir turbulence. That turbulence matters because moving waves that meet reflected waves can cascade into smaller motions. Smaller motions are easier to turn into heat. Jason Tenbarge of PPPL said this was the first experimental verification that the reflected energy could be enough to heat coronal holes. The results were reported in the Astrophysical Journal, so the wave camp got new strength, not final victory, but real strength. At this point, the mystery starts to look less like a courtroom with one guilty suspect and more like a crowded workshop. Waves are there. Reconnection is there, tiny jets are there, current sheets are there. The question may not be which one exists. The question may be which one matters most, where and when. That is a harder question, but also a more honest one. Stars are not simple. The sun has quiet regions, active regions, open magnetic fields, closed loops, and cycles that rise and fall over about 11 years. ESA says Solar Orbiter is trying to understand that full system. A single neat slogan may never cover all of it. Nature usually resists slogans. Would you share this video with one person who loves space but never hears the messy part of science? Sharing helps this story reach people who care about how discovery really works, not just how neat headlines sound. Because the real beauty of this puzzle is that the sun keeps forcing better questions. Here's one of those better questions. If the corona is so hot, why does space near it not feel like an oven? Because temperature and heat content are not the same thing. The corona is extremely hot, but also extremely thin. A single spark can be hotter than bathwater. That does not mean it warms the whole room. That is another place where everyday thinking can mislead us. We hear millions of degrees and picture solid walls of fire. But the corona is more like a ghostly high-energy mist. It would burn through particle energy, not through the thick, heavy heat you feel when you open a hot dishwasher. Thin does not mean weak. It means different. There's also the question of distance. NASA notes that the corona can be much hotter even though it is only about 1,000 miles above the surface in some comparisons. That number is tiny on solar scales. It is as if the rule breaking happens just one neighborhood over, not on the far edge of some giant invisible desert right above the visible face. And then there is the question of sound, though not sound your ears could hear in space. If you translated the motion into something human, the corona would not feel silent. It would feel tense, a humming wire, a snapping cord, a rush through pipes behind the wall. The sun's outer atmosphere is full of stored strain looking for a way out. When I think about why this story grips people, it is not only the temperature numbers, it is the insult to common sense. Fire should cool as you leave it, steam should fade away from the kettle, a halo should not outburn the lamp. The corona breaks that chain of expectation over and over again. And yet the sun is not cheating, it is just playing by deeper rules than the ones we learned first. The visible surface is not the only place where energy matters. Motion matters, magnetic fields matter, plasma behavior matters. Once those pieces enter the room, the paradox becomes less like a trick and more like a message. The sixth important discovery then may be a philosophical one. Scientists expected one elegant sentence to solve the hot corona problem. What they actually found was a layered answer, built from waves, reconnection, structure, timing, and region-to-region differences. The household comparison is cooking. A meal can be heated by flame, by hot air, by steam, and by the pan itself. The sun may use many burners. That does not mean anything goes. It means measurement becomes even more important. Which regions show steady brightness? Which ones show bursts? How much reflected wave energy is there? How often do nanojets appear? How much delay sits between a low brightening and coronal heating above it? That is why precise missions matter. Solar Orbiter can study the sun from changing angles and from as close as 42 million kilometers according to ESA. Parker Solar Probe can dive inward to about 3.9 million miles from the sun, according to NASA. IRIS can focus on small features. Hi-C can grab high-resolution looks during short flights. Each tool sees a different part of the elephant. The named institutions matter too because this is not one lonely scientist with a wild guess. NASA, ESA, Johns Hopkins Applied Physics Laboratory, the University of Chicago through Eugene Parker's legacy, the University of Colorado Boulder, NASA Marshall, PPPL, UCLA, Nature Astronomy, and the Astrophysical Journal. This is a worldwide, decades-long effort. And still, the sun keeps a little of itself hidden. That should not frustrate us too quickly. It should remind us what a real frontier feels like. A real frontier is not clean. It is full of half-won arguments, improved instruments, and moments where one new number rearranges 20 old ideas. That is exactly what is happening here. Some of the most exciting future work may come from combining these clues instead of choosing sides too early. A braided magnetic field may build stress. That stress may release in tiny bursts. Those bursts may launch waves. Those waves may reflect in regions with changing density. The reflected waves may stir turbulence. Turbulence may finally turn motion into heat. In other words, the hot corona may not be explained by one dramatic event. It may be explained by a chain, not one hammer blow, but many taps in the right order, not one huge fireplace, but countless little pathways carrying and releasing energy. That kind of answer is harder to fit in a headline. It is also more likely to be true. So when you see a picture of the sun now, try not to stop at the bright yellow disk. Picture layers. Picture the photosphere at about 5,500 degrees Celsius. Picture the corona reaching around 2 million degrees Celsius. Picture invisible magnetic ropes twisting through plasma. Picture a crown that is not passive decoration, but active machinery. And picture the time scales. A mystery recognized around a century ago, a crucial spectral answer in 1941, wave theory in 1947, nanoflares proposed in 1972, a key nanojet observation from April 3, 2014, a Parker launch at 7:31 UTC on August 12, 2018, a crossing into the corona in April 2021, fresh lab and telescope clues still arriving in 2024 and 2025. Would you leave one more comment with the part of this story that changed your picture of the sun the most? Commenting helps me learn which moments stay with you so I can build future videos around the questions you actually carry away, because this ending only works if the image in your head has changed. At the start, the sun looked like a simple fire with a confusing halo. Now it should look more like a living engine wrapped in a bright skin and crowned by a restless atmosphere. At first, the contradiction was the whole point. Now, the contradiction has shape. It has names, dates, missions, and clues you can hold on to. We began with something that sounded impossible, a crown hotter than the face beneath it. But what seemed impossible was really a sign that we were asking a surface question about a deep machine. The sun's visible light fooled us into thinking the visible layer must be the main story. It is not. The real story is that the sun stores energy in motion and magnetism, then spends that energy above the surface in ways we are still learning to trace. Sometimes it may spend it in waves, sometimes in tiny magnetic snaps, sometimes in braided current sheets, sometimes in reflected turbulence over coronal holes, maybe often in combinations of all of them. That is why the mystery has lasted so long. Not because scientists were lazy, not because physics failed, but because the sun is doing several hard things at once in a place that is hard to measure on scales that range from a few seconds to solar cycles. It is like trying to understand a whole city by listening through one apartment wall. Each new instrument opens another room, and yet we are closer than ever. We have touched the corona with a spacecraft. We have watched tiny jets flash. We have seen delays as short as 20 seconds between low brightenings and coronal heating. We have tested wave reflection in a 20-meter plasma device on Earth. The unknown is still there, but it is narrower now. It has edges, Giting. So the next time you see an eclipse photo, do not just admire the white crown, hear the hum in it, hear the plucked string waves Alfvén imagined, hear the tiny snaps Eugene Parker suspected, hear the quiet insistence of data from NASA, ESA, IRIS, Solar Orbiter, Parker Solar Probe, and labs on Earth. That crown is not just light, it is a question still being answered, and maybe that is the best ending this story could have. Not that we found one perfect line to shut the case, but that we learned the sun is stranger, richer, and more alive than the simple picture we started with. A few people once saw only a halo. Now all of us can listen for the engine inside it. The sun is not only burning, it is talking in waves, in loops, in jets, and in heat where heat should not be. And if you carry one image from this story into the rest of your day, let it be this: a white crown hanging in black space, not as a decoration around the sun, but as the place where the star whispers its deepest secret. Listen closely.